This strange picture I will explain at the end of the talk. But before we dive in to extrasolar planets, I'm going to start with a system of planets that I hope looks somewhat familiar. So on the far left, of course, we have our nearest star, that is our sun. And this is followed by four rocky planets where most of their volume is solid rock with a thin atmosphere. So that's Mercury, Venus, Earth, and Mars. And just in case you're feeling a bit befuddled today, you are here. And then after the rocky planets, we have this band of rocky, rubbly leftovers from the planet formation process called the asteroid belt. And then beyond that, we have the giants that are mainly gas. And that's Jupiter, Saturn, Uranus, and Neptune. And then at the end, we have the Kuiper belt, which, similar to the asteroid belt, is a group of leftover rocky, rubbly parts from the planet formation process. So from this system of planets, and these were the only ones we knew until the early 1990s, we came up with four rules of how to build a planet system. Rule number one, planets have approximately circular orbits. We don't in our own solar system see planets that are on very bent elliptical orbits where they swing through the inner solar system and then just head out into the outer solar system. No, their orbits are roughly circular. They stay roughly the same distance from the sun at all times. Rule number two, all the planets in a system orbit in the same plane. That is, we don't see them orbiting just any old direction around the sun. They all go in the same direction in a kind of disc-shaped piece of sky. Rule three, there are basically two flavors of planets. Now, there's some subtleties, but approximately you're either rocky or you're gaseous. And there is nothing in between those. They're the two choices. You're a rock or you're mainly gas. We don't see planets of all shapes and sizes in our solar system. Rule four, if you are gaseous, you are in the outer solar system. And if you are small and rocky, you are nearer the star in the inner solar system. We don't see a mix. It doesn't go rock, gas, rock, gas, rock, 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 gas. It goes rock, 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 gas, 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 gas. So based on these four rules, we came up with an explanation as to how planets formed. And that explanation starts with this idea. You start off with a young star, and that young star is surrounded by a disk of dust and gas. And this is where we're going to build our planets. And this instantly explains rule number two, because if you form everyone in this disk of gas, all the planets are going to end up in that same plane. So we start off with microscopic sized dust particles, and these steadily collide and stick. And eventually gravity gets excited enough about the whole business to pull the resulting body into something round that resembles a planet. And this explains rule one, because the best way to collide and stick so you can get bigger and bigger and bigger is if you collide very gently. And your velocity around the new star will depend on your distance from it. So ideally, you want to be in a nice circular orbit, moving along with other pieces of rock that are also in a nice circular orbit. So the speed difference between the two of you, between your nearest neighbours, is very low. So it's a gentle collide, stick, you get bigger. If you're on an elliptical orbit, you will swing in and out of the inner and outer regions, and you will collide with all kinds of material moving at all different speeds. And the result of that isn't a gentle collide and stick. It's like a major car crash. And so it's collide, bump, and throw apart. It's much harder to build up a large body that way. And there's proof. If this sounds too far-fetched, I can tell you, we've seen these disks. These are results from ALMA in the infrared, and they are all disks around young stars. So we actually think that basically every star you see at least had the ability to form a planetary system. Now, the next part is a little bit of extra physics, but nothing too surprising, because I'm going to say, if you are forming close to a new star, you're going to be hot. And if you're forming further away, it's going to be a bit chilly. And that means there comes a point where water vapor freezes into solid ice. And we call this the ice line, or sometimes the snow line or the frost line is all the same thing. And it's the point where water stops being a vapor and starts being a solid. So what that means is if you're forming closer to the star than the ice line, you are mainly dry grains of silicates and other rocky material. But if you form further out, ice joins in that game and gives you more building material. Therefore, if you form closer to the star than the ice line, you haven't got as much building material and you form a bit smaller. Whereas if you form further out, you get this sudden burst of building material from all the ices and you can become a lot larger. And so, slightly simplistically, this basically explains our two classes of planets. If you form in the outer solar system, you've got more building material, you can become larger. And if you form in the inner solar system, there's less around, so you're smaller. And so you have these two very distinct classes. And it also explains why the rocky planets are closer in than the gas giants. So until the early 1990s, these were all the planets we knew, and that seemed like a pretty solid system for understanding planet formation. Like there wasn't anything too crazy in there. All I actually did was tell you the stars were hot. It wasn't very controversial. So when we started to find other planets around other stars, it was assumed they would be similar. And this was totally wrong. So the first exoplanet that everyone actually remembers, which is not technically the first exoplanet, but it's the first one that was found that orbited a star similar to our sun. And this was a planet called 51 Pegasi b. And the discovery of this ultimately got the Nobel Prize in 2019, but the discovery was in 1995. But 51 Pegasi b was not really what we were expecting. So let's take a step back and ask how it was discovered. 51 Pegasi b was discovered not by my cat, but by a technique called the radio velocity technique. So when we picture planets going around stars, we picture a system like this. So the star, we believe, is stationary and the planet does all the work going around the outside of it. But in truth, the planet also has gravity and it pulls on that star and causes it to make a slight wobble. More accurately, both the planet and the star orbit around a common center of mass. It's just that that center of mass is very close to the center of the star, so it makes a teeny wobble, while the planet makes a much wider orbit. But because the star is much brighter than the planet, this wobble is detectable. And the bigger the wobble, the bigger the orbiting planet, because if the orbiting planet is more massive, it's going to pull harder on that star and force that center of mass further away from the star's center and therefore cause a larger wobble. So this technique gives you a planet mass. Most technically, it gives you a planet minimum mass. And this one was this was how we found 51 Pegasi b. Now, this planet is approximately Jupiter-sized. And you might say, okay, you said it was going to be surprising, but we've got a Jupiter, they've got a Jupiter. It's all the same, right? It turns out not quite. This Jupiter has an orbit around its sun-like star of just 4 days. It orbits at just 5% of the Earth to Sun distance. To put that in perspective, our closest planet, Mercury, is 40% of the Earth-Sun distance. And that's the nearest one we've got to our sun. And this doesn't make any sense. Because as we said, we expect only some dry, rocky material close to the star. And actually, the closer you get to the star, the less material there is because the star vaporizes a whole load of it. The really big building material comes much further out. So you expect small planets in, large planets further out, just like our solar system. But here we are, one of the first systems we've discovered. And we have this giant planet cushioned not just in the inner planetary system, but like way up close to its star. So we had no way of explaining this initially. And so therefore, the only logical thing to do as astronomers was to give this a name. And so we called this new class of planet a hot Jupiter because it's Jupiter, but it's hot. It's very, very logical naming. But how do these come about? Well, it turned out we actually did know. There was a theory about this possibility that came out some years previously, but there'd never been any evidence for it. So people sort of shrugged and walked away. But with the discovery of hot Jupiters, this theory came back to the forefront. And it goes like this. So here you are, you've got your disk around your young star, and you're building up that planetary material. And at some point, you reach a planet that's roughly the size of Mars. Now, Mars is not a big planet. It's only got a tenth of the mass of the Earth, and it's about half the radius. It's kind of squiffy, but it is nevertheless a planet, and it has enough gravity that it starts pulling on that gas disk that surrounds it. So let's take a top-down view. And what's going to happen now is as Mars forms, as something the size of Mars forms, it's going to pull on the gas that's closer to the star and the gas that's further away. And this turns out to be a bit like being in a race. So here we have Mario, Princess Peach, and Yoshi. And they are, for the purposes of this talk, tied together with a rope. Now, as they tear around the track, Yoshi's on the inner track, so he pulls ahead, and Princess Peach is on the outer, longer track, and so she holds behind. And therefore, Mario in the middle feels a force from both the inner Yoshi and the outer Princess Peach. And everyone does a spin. Yes, thank you. And this is sort of what happens when planet formation too. It feels a drag coming from both the gas outside it in a further out orbit and the gas inside towards the star. More accurately, it's not really tug force, it's an exchange of angular momentum, but the effect is very similar. So what happens typically, but not always, is that the force going inwards wins, and the planet experiences a drag force towards the star. So what that means is that you can actually form a giant planet far out where there's plenty of building material from all these ices and rocks. And then before this early protoplanetary disk of dust and gas has disappeared, it has enough gas drag on it to start pulling that planet in. And we call this migration. And so in the case of a hot Jupiter, these giant planets form and they're pulled all the way in towards their star to end up on very, very close orbits. And this is how we think hot Jupiters form. And this turns out to be a major sculptor of planetary systems. Even if there isn't a hot Jupiter, we strongly suspect planets move around a lot during their early years. So, okay, we've got this hot Jupiters, but we think we've cracked them. Then we discovered the first multi-planet system. So the first system with more than one planet. And this was Upsilon Andromeda A. Now this system has a hot Jupiter, but okay, we're okay with hot Jupiters now. We understand them. It has another planet that's on an orbit that looks like this. And it doesn't stop there. It's got a third planet, and that orbit looks like this. And this is really, once again, not making any sense at all. Because if you remember, we said, and we have observed, these disks around young stars where planets formed, which should have kept all the planets in the same plane, just like the solar system and on circular orbits. Because if they're on strongly elliptical orbits, it's very difficult to build a planet. So what's going on? Turns out gas is not the only way you can move planets around. And this simulation was done by, I think, a team at Northwestern University near Chicago. And they hypothesized the system actually once had a fourth planet, planet E. And initially everything was okay. Are we going to start this movie? Yeah, there we go. Okay, so these two planets formed, everything was hunky-dory. But then just through chance, as they orbited around, at some point, they got very, very close to one another. And as they did, they gave each other a huge gravitational kick that looks like, wait for it, that. And planet E was ejected from the system. But the push from ejecting planet E sent planet D onto a very different orbit. So you ended up with losing planet E and planet D being dragged onto this very elliptical orbit from the force of the ejection. And as it did, it started to pull gravitationally on planet C that was probably minding its own business until now. And planet C's orbit also started to distort. Planet B, the hot Jupiter, would have been saved from this because it was so close to the star, it only really cares about the star's gravity. And there's very little another planet can do to it. But planet C, further out, it got influenced by planet D, which was pushed onto this orbit by the ejected planet. So planet formation turns out to be a highly dynamic process, and you get some really weird results. So we've already trashed most of our initial ideas of planet formation. We don't always get circular orbits. We don't even always stay in the same plane. But so far, we've had basically gas giants and rocky planets. That's fine. So we're not going to break that rule, right? Well, yes, let's break it. Here is planet Gliese 1214b. Now, this planet was actually discovered not by the radial velocity technique, but by the second major technique for finding planets, and that is known as a transit technique. Now, in this case, you're relying on the system being more or less edge-on to where we're looking from Earth. And from that edge-on view, the planet crosses the star's surface. And as it does, it obscures a tiny amount of light. And if you build an instrument, such as the Kepler Space Telescope, that is sensitive enough that it can see that tiny, tiny dip of light, you can detect the presence of a planet. Now, for this, you don't get the planet mass. The mass doesn't actually matter. What matters is physical size. So the bigger and wider the planet is, the more light it will block out. And therefore, you can get a measure on the planet radius. Sorry, let me just do that. Okay. So if you are lucky enough, and it's not trivial to do this, but if you can get both a measure on the mass through the radial velocity technique, and you get to measure the transits, you can have a mass and a radius, and that, assuming a planet is roughly circular, can give you an average density, which tells you at least something about the planet itself, whether it's a gas or whether it's rocky, which are the only two choices, right? Except in this case, what we found was the planet was too dense to be a gas giant, but it was actually too light to be a rocky world. So what was going on here? It wasn't any of our two scenarios. It was something in between. Now, several options were considered for this planet, but when it was first discovered, one of the options that was considered was that, well, it could have a lot of liquid. So potentially, maybe this planet had just colossal oceans to make it a water world. So in this case, there would be absolutely no land available whatsoever, but the planet would be basically drowning under its own oceans, which is kind of amazing to think about. So this leads to an obvious question. Are water worlds habitable? I mean, water sounds good. We need it for life. So if there's lots of it, is it better? More life? Turns out slightly complicated. So for that, we have to understand a concept called the habitable zone, which is one of my most talked about and my most hated topics, because it sounds so promising, a zone in which you're habitable. I mean, surely if you're in the habitable zone, you have a habitable planet. But turns out not quite. So let's go back to what we know. If we do the radial velocity, we get a handle on the mass. If we can do transit, we get a handle on the radius. We also know the distance from the star, and that tells you how much starlight that planet is receiving. Is that enough to tell us whether the planet could be habitable? And the warning that it's not comes from our own solar system. On the left, we have an image of Venus, our neighboring planet, taken by JAXA's Zakatsky mission. Now, Venus is almost exactly the same radius and mass as the Earth. It's very slightly smaller, but there's not a lot in it. Of course, it's closer to the star. But that doesn't really explain Venus. So, for example, if we take the Earth and we ask what would its temperature be based purely on the amount of starlight received, the answer is a rather chilly average minus 18 Celsius. Now, fortunately for us, we have an atmosphere with gases such as carbon dioxide that trap heat. So our actual average surface temperature is about 15 Celsius. Now let's take Venus. Venus is closer to the sun. So based purely on sunlight, its temperature should be 27, which sounds pretty nice, actually. I quite like to go and hang out on a 27-degree planet. But we do know it has an atmosphere. Now, if it was Earth-like, we'd expect to lift that by, basically roughly 30 degrees. However, the actual surface temperature of Venus is a rather staggering 460 Celsius, because its atmosphere is not the same as Earth. It's thick carbon dioxide, and this gives you a much bigger thermal blanket. So even though it only receives a little bit of extra sunlight compared to the Earth, it's a much, much hotter planet. And this is where our problems come. We don't know the atmosphere of these rocky worlds very easily. And so therefore, we don't know where around the star would be the most habitable radius. So as a result, when we talk about the habitable zone in reference to exoplanets, we usually mean the Earth's habitable zone. That is, the orbits around a star where you could just drop the Earth in and it would receive enough starlight to keep its liquid oceans. So if it's going too far out, then it will freeze. And if it goes too far in, we lose the water and it evaporates. So it's the orbits in between those two boundaries. And the way we decide these limits is known, we actually use our carbon silicate cycle. So carbon silicate cycle, here is the Earth, and we have an atmosphere with some carbon dioxide, which is going to give us the carbon of the carbon silicate atmosphere. Now, as probably most people know, carbon dioxide traps heat. So if you have more of it in the atmosphere, you have a warmer planet, which is the problem when humans add carbon dioxide to the atmosphere. But putting aside humans, let's first take a planet like the Earth and put it just somewhere in the habitable zone. And then let's take a look at the surface. So here we have carbon dioxide in the atmosphere. Now, this can dissolve in rainwater, land on the silicate rocks, giving us the silicate part of the carbon silicate cycle, and become a solid. And eventually, this can return to the atmosphere through volcanoes. Now, supposing we grab our planet and we push it towards the outer edge, it's going to cool down because it's getting less starlight. However, as it does that, it actually starts dissolving less carbon dioxide in the rainwater, and less of it also reacts with the silicate rocks, because chemical reactions do better in warmer conditions. So as you cool it down, these chemical reactions also slow down. And that means carbon dioxide is added to our atmosphere because we're taking less of it out, and it can build up. And as it does, it gives us a warmer blanket and keeps our temperate conditions. Conversely, if we go to the inner edge of the habitable zone, then we can extract more carbon dioxide from the atmosphere because chemical reactions speed up. And we can therefore remove carbon dioxide and cool the planet down slightly. And this is how we define the habitable zone. But if you have a water world, this process gets disrupted. And does it even still work? Well, if the water isn't too deep, we suspect it might. It's not as good because you've covered up that land with an ocean, and the ocean responds more slowly than the air temperature to changes in conditions. But it's still possible to have a carbon silicate cycle with the seafloor. But because it's not as good, perhaps there wouldn't be very big life. It might just be microbes or similar, possibly. Now, if you get even more water, you have problems, because at that point you get something called high pressure ices that form on the seafloor, and that completely seals off the silicate rock. So at that point, you shut down volcanism, you shut down the carbon silicate cycle, and you can't control your temperature anymore. So your habitable zone shrinks basically to a single perfect orbit that chances are you're not going to be in. And even if you were in, well, the star changes brightness over time, so you're not going to stay in there very long. So for these planets, we suspect they're not a very good bet for life for a deep ocean world. But I want to say we could be wrong. So, for example, this was a paper done by two researchers who suggested that if you couldn't have a carbon silicate cycle like we have on Earth, you could actually have one that used ices at the poles of the planet to trap and store carbon dioxide, and it might be able to work as well. But these are theoretical and simulations. So we don't know unless we see a planet where it's working. But as I just said, for most of these planets, we've only got a radius or maybe a mass. So what hope is there? Well, as actually was alluded to in the introduction very nicely, we're currently we're on the brink between a detection era and the next characterization era. Detection era has been all about finding these planets. Characterization is now about trying to find out something about them. And for that, we're going to try and look at the atmosphere. So this is a technique called transmission spectroscopy, and it's going to be the one that's going to be most in the news in the next coming decade. And the idea here is that molecules in the atmosphere absorb different wavelengths of light. So if you can look at light going through a planet's atmosphere and see which wavelengths are missing, you know, or at least you can make a solid guess about what molecules are in that atmosphere. So this is a huge challenge. If you have a star like the one on the right, see that tiny blue blob might be a terrestrial planet. This is a huge exaggeration of what the atmosphere is around that planet. And we're trying to get the photons that graze through that tiny atmosphere. And we need lots of them because we need to look at different wavelengths. So if we do a zoom up, here's our planet with our atmosphere. It's got different molecules. It might have carbon dioxide, it might have methane, it might have water, it might even have some biosignatures. And we're trying to catch enough wavelengths of light that we can tell which ones are missing and which ones have been absorbed. And it's immensely difficult, especially for rocky planets like the Earth. But there are instruments that are trying this. The JWST is trying this. And Ariel, which is an ESA-led mission that will launch, I think, at the end of this decade, is going to try and do a survey. It's not of Earth-like planets, but of smaller planets, and try and find out something about their composition. So if you do this and you measure how much light is absorbed at lots of different wavelengths, you get something that we call a spectrum. So in this example, for example, these peaks might all mean water in the atmosphere. And this is a real spectrum. It was taken by the JWST of a planet called WASP 96b. Now, WASP is not habitable. It's a gas giant. But the fact we can even do this for a gas giant is incredible, and our techniques are getting better and better. So this is going to be what exoplanet science is about for the next coming decades. So I'm just going to end with this very strange diagram I showed you at the beginning. We often say, oh, we found an Earth-like planet. What we actually mean is we found an Earth-sized planet, because that's all we know at the moment. So it's not necessarily going to have a Starbucks on it. It could be very uninhabitable. But this discovery, this journey to find out more about these planets, this is the journey of our generation. And it's going to be our journey in the coming decades. Thank you very much.